So I hope my screen is visible now. Okay. Okay. So I hope everybody has gone through the lecture one of the course, right? So let me know all of you first. Where are all of you from and what all of you are doing? So can anybody start, volunteers, and let me know? So who all are you in BTech right now doing UG? Okay, so let me introduce myself first. So let me turn on my camera. Yeah, so am I visible and audible at the same time, right?
Yes, sir.
Yeah, great. So let me share my screen. Yeah. So I am Jitendra Kumar, and right now I am doing my PhD at IIT Bombay. Okay, and further, what my core area? So I work in motor design, particularly, and power engineering is my main background, and basically I work on motor design for electric vehicles. And we will discuss, some numerical problems along with theory, which you couldn't get through the lectures, and you have some doubts and questions, so you can ask here. And along with that, we will try to, cover what do you want from this course. We can discuss, what type of questions do you want. Uh, what is your objective for, doing this course? Uh, I hope many of you might be, preparing for GATE exam or some other exam, or some of you might be doing this for, improving knowledge in this subject. So that the objective of live session is to, what you couldn't get through the recorded lectures, that we we could provide through this platform. And if there is any doubt, please let me know. I hope I am able to clarify. So, could some of you also volunteer and start discussion? Otherwise, we can start the questions straight away. So, in first lecture, let me start. Okay. In the meanwhile, in between, if you feel that we should discuss, we will please stop me and we can discuss. So in today's lecture, we will see about PMMC and electrodynamometer type of instruments. So what are the difference between them? What are the difference between PMMC type of instruments and electrodynamometer? So do you have any idea, anyone? So basically, in name itself, it is mentioned what is PMMC and what is electrodynamometer. So first PMMC is, let me start writing. So PMMC, you might be looking for the questions of the week one. I hope you might have received, or the quiz one questions are unlocked for you guys. So most of the questions would be based on PMMC, electrodynamometer, moving coil, moving iron type instruments, repulsive type, attractive type. Okay, so I hope such type of questions you might be seeing, right? So PMMC is nothing but, what does it stand? Could anybody tell me what does it stand? PMMC means, the full form of
Permanent
PMMC.
magnet moving coil.
Right. Great. Correct. So permanent magnet moving coil. So one thing is for sure, in this instrument, permanent magnets would be there, right?
Yes, sir.
Right. So uh, the the property of permanent magnet is, why do we use permanent magnet anywhere in electrical devices mostly? Like you might be hearing somewhere that in electric vehicles also permanent magnets are there, or motors also permanent magnet motors, or anywhere. So in electrical devices, permanent magnets. Why do we use permanent magnets? Do you have any idea? So magnet will produce magnetic field, right? And we use, in electrical machines, we use magnetic field to produce, to maintain magnetic flux, to provide magnetic field to the instruments, so that there will be some magnetic force, right? So flux, why the flux is necessary? So flux is necessary there, anywhere, to produce some force, right? Flux is a, we cannot see flux, um, but it is there. When you place permanent magnets north and south poles together, there will be flux originating from north pole, right? So flux is going from north pole to south pole. Okay, and if we are placing some magnetizing material, such that iron or so they will experience the flux whichever is originating from north to south. Okay, so let's suppose this is iron, and it has some number of turns, right? So let's suppose n number of turns. Okay, so how much force will be acting on this rectangular block or iron? What should I write here? How much force will be there acting on the iron pole, you can say, or this material? So according to Lorentz law, it should be IL cross B, right? And
Yes,
if,
sir.
yeah, and if the current is flowing in such a manner, right? This is, consider this as a coil, then the force L cross B. So here, this is L vector, and this is B. this is B, right? Because magnetic field is established in this direction. So this is B vector, this is L vector. So L cross B, if you curl your finger like this, L cross B, the force will be in which direction?
Inside.
This is L, this is B, force
In
is inside. Yeah, great. Similarly here, if you curl on the right hand side, so L cross B, so it will be here
outside.
in
Towards
outside, right?
outside.
So there is force, there is force, there is the tendency to generate some EMF there. And if there is some EMF and if you provide some current, there will be some power as well. So right now we are concerned with torque here, okay? And let's draw one more circular block. Okay, let's suppose coil is like this. Okay, so here we got for this rectangular thing I LB. If L cross B and L cross B, if it is placed as this fashion, whatever I have drawn, then L cross B sine theta. So the angle between B and L vector is how much right now? B is in this direction and L is in this direction, right? So this is 90 degrees. So it is maximum, right? So it will be ILB. Okay. And what about torque? Torque is nothing but R cross F, the basic science, if you recall from class 12.
Force into
Okay.
displacement.
Right. And this block will have the tendency to apply the force this side. So R into F, if you calculate the torque, so ILV is force into R. So L into R of this is R, this is L. So L into R of this is area, so IAB. Okay, so this is nothing but your torque. So if we consider that there is only one term. If there are n terms of the coil, then we will also have to include the n terms in this expression. Right? Then total current will be n into I. Right? MMF. I hope you remember MMF is nothing but n into I. Okay.
Right. Right, sir.
Right. So this will be total torque. Okay. And similarly for circular thing, this area will be how much? This
Pi r square.
pi r square. So this area will be pi r square for circular thing. So you can plug in it here in area. Okay. Now there was one question that why these magnets are kept like this, kept like cut in this fashion. Why not they are in rectangular fashion? So do you have any answer for that? Why they are like that and why we do not design it like that in this fashion, a square? So see, we have we have core material placed it over here, right? So we want it to face maximum amount of flux. So the more amount of flux, more amount of magnetic flux density. So B should be, highest, right? On the other hand, if it is rectangular, then some of your flux might go and they may never link to the iron material. So that will be wasted, right? So we want to fully utilize our permanent magnets. As you know, permanent magnets are the most costliest component in these instruments, right? So, so that is why we go with electrodynamometer. So in further we will see in electrodynamometer we have at the place of permanent magnets we have coil which is used to produce magnetic field. So electromagnets basically what we call them. So electromagnet is nothing but the same amount of flux will be produced by the coil wrapped on a coal. So coil will produce the field and we can avoid permanent magnets. Okay. So I hope I am clear. And this type of instruments, this PMMC type of instruments, they will have some spring. So whatever this torque will be produced with the help of this electromagnetic properties, that will be balanced with the help of a spring. So when your needle will move, so there will be one spring tied to it, and that will apply force in the opposite direction. So a spring force or the spring torque because of a spring force, torque because of a spring force will be how much? K into theta. Theta will be angle if let's say your needle is at 0 degree and at 90 degree, and let's suppose your needle is placed here. So this needle will have to move, right? And this needle will move according to this torque, whatever is applied, that expression we have derived, IL into B into N, and it will be balanced with K theta. So this is the theta. So let's suppose your needle has come over here. So this is 45 degree. So K into 45 degree equal to B into A. So this will be your, deflecting torque is equal to a spring torque. Basically, at equilibrium, this spring will be, or this needle will be standstill. Okay. So you can calculate theta also, K also. K is nothing but a spring constant. Okay. So that is how we generally calculate. And in galvanometer, we generally see this PMMC type of instrument could be anything. So generally, if you see in galvanometer, we consider T is equal to Ki. K is nothing but VAN into I. So this is nothing but your galvanometer constant Gi. So we will solve one question based on that, what we have. So let's suppose I'm writing question. PMMC instrument is there, okay, which has 200 turns, right? And length of the coil is equal to 1.5 centimeter, okay? And width of the coil is 1. Again 1.5 centimeter, okay? And a spring constant is also provided. K is nothing but a spring constant. Let me also write it, otherwise you might confuse it with galvanometer constant. So a spring constant is how much? A 1.75 micrometer meter per degree. Okay. So further information is the resistance of the coil is 100 ohm, and we need to calculate the deflecting torque. How much will be the deflecting torque? So this type of questions you will face in your quiz 1 or maybe in exam also. So how much will be the deflecting torque? Oh, what? Yeah. So how much will be the deflecting torque? Just right now we saw it is nothing but VA into N into I. Okay. And yeah, air gap flux density I forgot to mention. So air gap flux density is 0.9 Weber per meter square, and current is flowing as 4 milliampere. So we just need to plug in all those values. B is nothing but 0.9 into area is length into width of the coil, so 1.5 centimeter into 1.5 centimeter, right? And number of turns are 200 and current is 4 milliampere. So how much will it be?
0.01.
0.01,
08.
0.0108 unit. The answer is actually 162 micronewton meter. 162 into 10 raised to power minus 6 Newton meter. Is anyone getting this much?
1.62 into 10 power minus 4, sir.
1.62, yeah, exactly. 1.62 into 10 raised to power minus 4. Yeah, great. Yes. Okay, so this was very basic question. Just we needed to place in the expression or plug in all the values and you'll get the answer, right? Now, the second part of this question is how much is the sensitivity of this PMMC instrument? So we need to calculate sensitivity. So what do you mean by sensitivity, first of all? Has anyone any idea? So sensitivity is basically, per unit current, how much the pointer is moving, right? So let's suppose for 1 ampere or 1 milliampere, how much degree the pointer is moving. Okay, so that is what we mean by sensitivity. So um, let's suppose um, we will calculate the deflecting torque for 1 milliampere first, okay, and we will calculate deflection. Can we calculate deflection? We have these much data, so can we calculate deflection of the spring, or sorry, of the pointer, how much it will deflect from its origin? So for 1 milliampere, because all these instruments will have very small amount of current, that is why I am considering milliampere. Otherwise, for high current instruments, you could or you should consider ampere, right? So for 1 milliampere, the deflecting torque will be same, just just at the place of you know 4 milliampere, we will have 1 milliampere. So 1.62 divided by 4 into 10 raised to power minus 4. So it will come out to be 40.5 micronewton meter. So this much is deflecting torque there for 1 milliampere. Okay. And we have another data that a spring constant. Okay, so we want in terms of degree, and a spring constant is in Newton meter per degree. Rather, it is micronewton meter per degree, right? So 1.75, 1.75 micronewton per degree. So 1.75 into raised to power minus 6 Newton meter per degree. This is a spring constant K into theta is equal to 40.5 into 10 raised to power minus 6. Okay, so theta will be how much? 40.5 divided by 1.75. So theta will be approximately 23.14 degree. Reflection in the pointer. I hope everyone is getting this much, 23.14 degree. So this much deflection will be there per milliampere. So if you provide these instruments with this much of current, sorry, 1 milliampere of current, okay, so you will get deflection of 23.14 degree. So could anyone let me know whether this PMMC device is linear or non-linear? So let me again show you the expression T is equal to K into theta. So torque is linearly dependent on the position. What do we call such devices? Linear or non-linear?
Linear, sir.
Linear device, right? So PMMC devices are linear device. Okay, great. So we will move further ahead with another question. Hmm. So the next question is we need to calculate the full scale deflex. Full scale deflection. What do we mean by full scale deflection? So full scale means, it will reach at its maximum value. The pointer will reach at its maximum value. That is nothing but 90 degree, right? So we consider this as 0 degree and this as 90 degree. So to reach that much position, we just saw that for 1 milliampere, it will reach 23.14 degree. So for 90 degree, how much current will be required? So it is just a linear expression. So for 90 degree, it will be required 90 divided by 23.14 degree per milliampere. So it is very simple. 90 divided by 23.14, that would be approximately 3.88 milliampere. Isn't it? Does anyone have any doubt in this or any earlier part anywhere?
No.
Great. So let's move ahead. Now we will talk about damping. Okay, so why damping is required in such type of instruments? Damping. Why it is required? So if damping will not be provided, then what happened that if you apply some torque, the pointer will have the tendency to oscillate. Okay, and in control system or somewhere you might have studied that there are three types of oscillation or damping, right? What are they? Underdamped, critically damped, and next one is
Overdamped.
overdamped. Great. I I think you have already heard this type of damping, right? So overdamped. Where did you study those dampings? Most probably in control system, I guess, right? So what happened in underdamping? In underdamping, your system may never settle down, right? So it will keep oscillating. And in control system terms, these underdamped systems are considered as unstable system. Okay. Next, critically damped. So this much damping is sufficient enough to settle the pointer, right? So this much is exactly the amount of damping that is required to bring the pointer in a stable condition or a steady state. Another one is overdamp. So overdamp is what the damping torque is provided more than enough. Okay, so that your your pointer will come to a steady state soon. So desirable is critically damped and overdamped. We do not want to have the system to be underdamped. Okay. So have you gone through the lecture where it is mentioned about damping of the system? So what are the dynamic equations? Do you know? There are dynamic equations of such any moving device, right? So what are they? Could anybody let me know? What is the dynamic equation of any moving devices? Mhm. Okay, so since we are applying some torque on the needle, okay, so this torque will be having some acceleration. So this acceleration we can write it as jd square theta by dt square. Okay, so first torque is nothing but damping torque. So td theta. Second one would be a spring torque, tc theta, and third one will be deflecting, deflecting torque. So all of them depend on theta somehow. Okay. So how they are related with, you know, theta is nothing but position of a spring, position of pointer from the origin. Okay. So j d square theta by dt square. Further we can elaborate. So deflecting torque is nothing but k theta. Sorry, deflecting torque is nothing but uh, I sorry BIMA. Mm, or we can write it as, you know, TD at I. Sorry, here I mistakenly, by mistake, I wrote with theta. So deflection torque, it depends on current, not on theta. Damping torque, next will be spring torque, that is k theta. And damping torque depends on d theta by dt. Some damping constant into d theta by dt. So now these three torques, they have different relationship between position, speed, and current. So on the speed, so damping will eliminate the oscillation in the speed of the pointer, A spring will have a relationship with the position of pointer, and deflection torque will have relation with current of the point, velocity. Okay. So the standard dynamic equation is a d square theta by dt square. Okay, and yeah, of course, sine we did not consider it, minus because they will be opposite to acceleration. Why I am considering minus signs here? Because all the damping torque will act opposite to the deflection torque. Okay. Similarly, a spring torque will also act opposite to the deflection torque or acceleration. So the standard equation is nothing but a d square theta by dt square plus b d theta by dt plus c theta is equal to td of I, so deflection torque. Okay. So here a is nothing but moment of inertia. B is nothing but damping constant, and C is nothing but a spring constant. Okay, so if you sometimes TD, you can write it as ZI. If you are given in this form, so you can calculate. There will be one condition. A solution of this type of differential equation is theta of t is equal to a e raised to power alpha 1 t plus b e raised to power alpha 2 t, as you might have seen in lecture as well. So, and if you find out alpha 1 and alpha 2, they will be root of this differential equation. That is nothing but minus b plus minus under root b square minus 4ac divided by 2a. Okay, so this will they will be the root if b square is higher than 4ac. If b square is higher than 4ac, then the system will become underdamped, overdamped. What will it become? If b square is higher than 4ac, then the other root will be, complex conjugate. Both roots will be complex conjugates. So it will be underdamped. Right? Is there any doubt? Please let me know. Please stop in between if you feel any doubt is there. Are you getting it? This equation? So what will be the condition? If you are getting it, what will be the condition for critically damped? In terms of b square and 4ac, will it be higher, lower, or equal to each other?
Equal to.
Equal to, right? Great. B square is equal to 4ac, then it will be critically damped. And if B square is, you know, less than 4ac, then it will be overdamped. So does anyone feel that I have committed some mistake? Why? Because B square, if B square is less than 4ac, then complex conjugate roots will be there, right? Not other way around. If B square is higher than 4ac, let me elaborate it further. If B square is higher than 4ac, then both the roots will be real, right? If B square is higher than 4ac, both roots will be real. right? So here they will be, over damped, right? So the classic way to identify is your roots should never be complex conjugates, to be it either over damped or critically damped. And here, if B square is less than 4AC in this expression, then your alpha 1 and alpha 2 will be complex conjugates. So here they will be under damped. Okay, is it clear? Both roots will be complex conjugates. And what happened critically damped? What will be the relationship between both roots? Will they be real or complex, or real and unequal, real and equal? What type of nature will be there? So basically, B square is equal to 4AC. So second term will die down. So we will left with only one term. So real and equal, right? Am I correct? Okay. So in electrical format, we provide damping, and that is known as eddy current damping. So what basically we do, we connect with some external resistance, right? And that external resistance will provide some. So how does this happen? Let me show you. So let's suppose there are poles north and south, right? And there is one coil with number of turns. Okay, this magnetic flux is passing, cutting it. Okay, with these coils we connect some external resistance. Okay, then what will happen? Since this coil has some flux, and as I showed you earlier, it will have the tendency to create some EMF, right? If any conductor is cutting some flux, there will be some EMF, right? According to the Maxwell law, or you know, and this current, there will be some current flowing in this circuit. Okay, so along with this current will be flowing along with some force, and this force is also, as I showed, it is acting in this direction. And with this force, there will be tendency, because force is acting, there will be acceleration, and there will be some velocity. And as we know that damping torque is dependent on d theta by dt, isn't it? So if we are concerned with damping torque, we will have this angular velocity. D theta by dt is nothing but angular velocity. And okay, since force is being acting there, so there will be rotation like this. And there is some EMF being generated. What will be the magnitude of EMF there with this process? How much the magnitude of EMF will be generating? So conductor is cutting the magnetic, first thing is magnetic flux, right? Conductor is cutting the magnetic flux density of B, and this is nothing but L, and this is nothing but R, right? This is 2R. So if the center is here, this is 2R. So on one side, if you see, this is one conductor, and this is second conductor. And these are generally overhang we consider, right? So for one conductor, it will be R d theta by dt. Okay, L into R d theta by dt. So the final equation of EMF per conductor is nothing but V into L into R d theta by dt. Okay, what is R d theta by dt? I guess you might have some doubt. What is R d theta by dt? So from the basics, if you recall, the equation of EMF is nothing but V into B cross L, right? This is motional EMF. Do you recall this expression?
Yes, sir.
Yeah, if you try to relate both equations, what are the similarities? B is as it is B, right? There is no difference in B. L is also same. The difference is only in the linear velocity. And what is the linear velocity? dx by dt, right? And in circular motion, dx by dt, x is nothing but r into d theta, right? X is nothing but r into d theta. And dx by dt is r d theta by dt. Now you got it? You should ask at every step if you do not understand. Okay,
Okay, sir.
right. So now tell me, what is the EMF per conductor? Because this will be one conductor. Okay, this will be another conductor. If there is only one term, I am just considering only one conductor. So how much will be the EMF there? EMF for induced in one conductor will be nothing but V L R d theta by dt. Now, EMF induced in one turn. What does comprise one turn? How many conductors in one turn? One turn means two conductors, right? See, this is one conductor, this is another conductor. They both are joined with wires. So this is making what? One full turn. One turn is equal to two conductors. Did you understand now why I am taking two conductors? Yeah,
Okay,
so
sir.
now total EMF will be, yeah. So here, as we saw in the beginning of the lecture, it was dot, right? And it was cross. So this EMF, if we consider plus and minus, that will be 2 times B L R d theta by dt. If there is n turns, EMF induced in n turns, how much EMF will be there? 2n, we will have to multiply with n, B L R d theta by dt. So this much EMF is induced if we place our coils in such a fashion. So this much EMF is getting induced here. How much? 2 L R B d theta by dt into n, right? So this much EMF is getting induced here. And if you have connected some resistance in this circuit, there will definitely be some current flowing in this circuit. Am I correct? And the expression of that current will be nothing but 2N RLB d theta by dt divided by R. Okay. So I hope you understood. And this, now we will talk about this resistance. So this resistance will comprise of coil resistance. This R will be equal to coil resistance plus some external resistance. So this external resistance we use for damping, or we use to, tune the damping, whether we want over damped, under damped, critical damp. We will also see the condition for that. But this external resistance is crucial to tune the damping. I hope you are getting where I am heading towards. So this is the current. This is the current we have derived. Okay. So we will come again back to our torque because of current. Let me turn on the light. Yeah. So now we will go back to our expression of torque, that is nothing but BAN into I. Okay. Now I, we have derived it here, and we will plug in the value of I again. So BAN, and this I is nothing but 2N BRL d theta by dt divided by R. Okay. And this 2 into R into L, we can consider it as area of the conductor, because see why I'm saying area, because this is the 2R, this is the 2R, and this is L, right? This is L, this is 2R. So the area of this rectangular conductor will be 2R into L. So this is the area. So if we further simplify it, BAN square into d theta by dt divided by R. So what type of expression it is making? What type of torque it is giving you? Since this torque is dependent on d theta by dt, right? So what type of torque it is? This is eddy current damping, and this is the damping torque. Are you able to relate this damping torque when I said that damping torque will be dependent on d theta by dt or velocity? It will damp down the velocity. And what will be the damping constant here in eddy current damping? What will be the damping constant? Anyone?
d theta by dt.
No. D theta by dt is velocity, right? Angular velocity. So damping constant
BN
will be
square upon R.
exactly BAN
Right.
square by R. So this damping constant is dependent on R, right? So how much R you are providing, that will determine what is the nature of damping in your circuit or in your instrument, right?
Yes, sir.
Externally, right? Because once you, why doesn't it depend on B or A or N, or why we consider them as a constant? Because once you have placed the permanent magnet in the instrument, your magnetic flux density is fixed, right? Area
Yes.
is also fixed because you have set out to your core, and number of turns also fixed. You cannot change it. But resistance is
Yes.
something you can vary every time. Yes. So that will, tune your damping, how your damping will work. Okay. So
Yes, sir.
the more R, the higher the value of R, the nature of or the damping will be a smaller, right? So if you want a smaller damping, then you will have to provide more resistance. So let us go back to our questions, what we were solving. What is our question there? So in this question, okay, so in our question, it is provided that if, because uh, in our main statement, we were provided with some resistance that was 100 ohm. Okay, so see, the coil resistance is 100 ohm already given. Okay, we solved this question, the coil resistance was 100 ohm. Now it is saying that when we add additional 100 ohm in external circuit, just the way I showed you, yeah, so this external resistance, it is saying that if we add, sorry, additional 100 ohm in this circuit, then this instrument exhibits the critically damped oscillation. So let me write this as a statement. So if we provide additional R external as 100 ohm, this circuit, then this instrument exhibit critically damped oscillation. Okay, we need to find out the critical damped constant. So we need to find out what critical damping constant. So what will be the expression of critical damping constant? So critical damping constant is the constant at which the damping torque is the critically damped torque, which means at the expression what we have derived it here, where did it go? Yeah. So this is our expression, right? This is the damping constant expression, and this damping constant will have BAN square divided by R coil plus R external. So B we know, right? B we know how much it was, 0.9 Weber per meter square. Area we were given, length was 1.5 centimeter, width was 1.5 centimeter. N is given 200. We'll have to take a square of whole divided by R of coil was 100 ohm. Now again we added 100 ohm externally. So this will be your critically constant critically damped constant. So you have to calculate this value and let me know what is the value of critical damping constant. Okay. Sorry, there is some noise there. Please repeat it. Or you could also type in chat box. There is some noise coming from your side. Yes, Sanjeev, go ahead.
820 into
8.
10 to the power minus 8
8. Okay,
Yes.
so this is the damping constant you are saying.
8.2
Anyone else?
8.2
Sorry,
into 10 to the power 8.2, sir. Into
8.2
10
into
to the
10
power
into power
minus 6.
minus 8. Minus 6. Minus
6, sir.
6. Okay. Minus 6. Yeah. Minus 6. Okay. And the unit?
It, uh,
Unit is very simple. Just equate with torque. Torque is equal to torque divided by d theta by dt. So degree per second and Newton meter. So this will be Newton meter per degree per second. Okay. But 8.2 is, I don't think it is. Yeah. It is correct. Yeah. 8.2 is correct. If you are considering, if you, so this unit you will have to take care, right? So this is not degree, then it will be radian per second. So unit is very important. In exam you perform all the calculation, you know all the concept, and at the end, if you mess up with unit, then you are going to lose some marks there. So Newton meter per radian per second. If you want to convert into degree, then you will have to multiply it with pi divided by 180, and that will give you, some Newton meter per degree per second, isn't it? So any doubt?
No, sir.
Great. Yeah. Okay, so this is it. So I hope you are clear about all damping. How does damping work? We will again revisit this damping topic. Okay, so there is no issue with that. Now let us go to the question further. Now we will try to convert our PMMC instrument as, or we will try to rather use our PMMC instrument as voltmeter or ammeter. Okay, so how to use like that? That we'll have to see. So let us suppose we want our ammeter with the range of 0 to 100 milliampere. Okay, we want our emitter with the range of 0 to 100 milliampere. We want to convert our PMMC instrument as an ammeter with the range of 0 to 100 milliampere. Okay, so what we will have to do? We will have to connect some resistance, that is for sure. Whether in series or shunt, that we will have to decide. What do you say?
Series, ammeter series.
No. Unfortunately, in ammeter, we will have to connect our resistance in shunt to this. So this
Right,
is
sir.
PMMC. This will have some internal resistance. Okay. So there will be one resistance. Shunt. For voltmeter, we connect them in series. Okay. So do not get confused with voltmeter and ammeter. In ammeter, always shunt. In voltmeter, in always series. So how are we going to convert it as ammeter? So we know that we will use one shunt resistance, but what should be the value of shunt resistance? That we will have to calculate. So what should be the value of shunt resistance? So see, what should happen? What should happen ideally? That this PMMC range was this full scale deflection of PMMC. We have calculated, right? How much was it? We have calculated earlier in question, right? Full scale deflection. Do you recall 3.88 milliampere was the full scale deflection current? Right?
Right, sir.
Yeah, so full scale deflection current was 3.88 milliampere for PMMC device. Now, when we have to convert it as an ammeter with 100 milliampere of full scale current, right? So when 100 milliampere of full scale current will flow here, 100 milliampere, then this PMMC should have 3.88 milliampere. The remaining current will go into the shunt branch. That will be how much? 100 minus 3.88. That will be nothing but some 96.12.
6.12.
Yeah, 96.12 milliampere. Okay. So now the shunt current we have calculated, right? And what will be the shunt current? So we know this current, we know this current, we know this current. So we can apply current division rule. Okay.
Current division rule.
Yeah. So 3.88 milliampere is equal to 100 into we know this 96.12, right? And 96.12 into R shunt plus this 100 ohm. This 100 ohm of the PMMC coil was given, right? This 100 ohm we forgot to mention here. So this 100 ohm, 100 into R shunt divided by R shunt plus this PMMC coil resistance, that is 100 ohm. Am I correct? This is the current
Right.
division rule. The current flowing here will be equal to 100 into this resistance R shunt, right? 100 into R shunt divided by R shunt plus R coil. So now we will have to solve it. R shunt, you will have to let me know what is the value of R shunt by solving this.
Four 4.03.
4.03 ohm. 4.03 ohm. I hope everybody is getting the same value. Anyone else? So 4.03 is the correct answer. So you just make sure that you are getting the similar value. I hope you understood the concept behind, converting the PMMC instrument, how to convert a PMMC instrument as a meter with certain range. So please do not make any mistake in exam. I hope you will be able to do it. Okay, or in some assignment questions also you will be able to solve. Okay, let us move forward. So the most important question is this above ammeter, what we have just calculated. This ammeter is what? What type of damping this ammeter possesses? Critically damped, over damped, under damped. What is the nature of damping in this ammeter? So for critically damped resistance, we had we have calculated, right? Or in the last question it was provided that if we will have total external resistance of 100 ohm along with coil resistance of 100 ohm, so total 200 ohm of resistance was required to provide critically damped. So critically damping resistance was 200 ohm. Okay. So now first thing is what we'll have to do. We'll have to calculate the total resistance of this ammeter. First, the first and foremost task is to calculate the total resistance of this ammeter. How much is that? How much is the total resistance of this ammeter? This is 4.03 ohm. This is 100 ohm. So if you calculate
20.
equivalent resistance, sorry, how much?
Less than 4.03, sir.
Less than 4.03. That is for sure, and that is enough for us, isn't it, to determine the nature of damping. So this ammeter resistance is less than critical damping resistance. So what does it mean? What does it imply? What will be the nature of damping in this ammeter? So let us again go back to our expression of damping torque. Where did it go? Hmm. Yeah, so this is the expression of damping torque, right? VAN square divided by R d theta by dt. So this R is getting reduced, man critical damp. So this torque will have the more value of the damping torque, critically damping torque rather. Isn't it, Niranjan?
Increase.
Yes, yes, sir.
Yes.
Increase.
Yeah. So it will increase. This damping torque will increase, and this will make the system what? Under damped or over damped?
Under them, sir.
Okay. Anyone else has any different opinion?
तो ओवर डैम्प लग रहा है, इंक्रीज होगा तो ओवर डैम्प.
Exactly. Yes. Over damped ही होगा. This will be over damped because the damping torque value is higher than the critical damping torque. So it will be over damped. So as I mentioned while deriving this expression as well, that when the value of resistance is going to reduce, then this torque will be higher than the critical damping torque. So it will be over damped. Okay, so where did it go? Yeah. Yes. So this much was sufficient for us, that equivalent resistance is less than 4.03. We do not need to waste our time in calculating equivalent exact resistance of this ammeter, and this R equivalent is less than critical damping resistance, which was how much? 200 ohm. So 4.03 is 200 is less than 200 ohm, and torque is nothing but VAN square divided by R d theta by dt. So since resistance is getting reduced, our damping torque is getting increased, and we will have over damped oscillation. Over damped oscillation. Okay, so I want to make sure that all of you have understood the concept of oscillations, right? Under damped, over damped, because it it might create some tricky questions in exam, so you will be able to handle those type of questions. Do not get confused. Okay. Similar thing we will perform for voltmeter as well. So what do you expect in voltmeter? Generally in voltmeter we connect a series resistance there, right? And that typical value of those resistances are very high. Very high means in order of thousands. And since we have the resistance of 100 ohm of coil in order of 100 ohms, So generally, the oscillations in voltmeter are under damped because the resistance is way higher than the critical damping resistance. So let us see that through a problem as well. So the yeah, go ahead. Okay, so the question is we need to calculate the series resistance to convert this PMMC into voltmeter of range 0 to 25 volt. Okay, so how to convert it? How to convert it? Let me draw the circuit. This will be our series resistance, and this is our PMMC with this external resistance of 100 ohm. Okay, and the current, the full scale, because since we are converting into some instruments, so we will have to consider always the full scale value. Like full scale value of this voltmeter is 25 volt, isn't it? So full scale current is 3.88 milliampere, right? So the total resistance we want to have, like when 3.88 milliampere is flowing, we should have the reading of 25 volt in entire circuit. So this voltage value should be 25 volt. Okay. So this 25 volt should have how much? 25 volt, just we'll have to apply KVL. 25 volt is equal to IR. So 3.88 milliampere into 100 plus R series, isn't it? So 100
Okay, sir.
plus R series is nothing but 25 divided by 3.88 into 10 to the power 3. So 25,000 divided by 3.88. So what is the value of 100 plus R series? So R series will be nothing but 25,000 divided by 3.88 minus 100. So what will be this value?
Six thousand 304.9.
Sorry, could you please repeat it again?
Six three four
6,000,
three point
63,
6,343.29.
43 you are saying? 0.29.
Two.
Okay. Anyone else?
Right, sir. Right, sir. आवाज नहीं आ रहा है सर।
साउंड नहीं आ रहा है सर।
Yes. Please let me know whether am I audible now.
Yes, sir.
Yes, sir.
Great.
Yes,
Great.
sir.
Thanks a lot. Thanks a lot for letting me know. Yeah, Jyoti, you had raised your hand for any question or for audibility. Okay. So, please let me know where did I got disconnected. Let me share my screen. So, till this value 6349, 6343.29, we were there together. After that, I asked whether this damping will be critically damped, under damped, or over damped. So we know this resistance is way higher, right? So this resistance will increase, and that will reduce the damping constant, and that will reduce the damping torque. In this voltmeter, okay, in this voltmeter, this damping torque is less than critical damping torque. So what kind of oscillations will be there? What kind of response of this instrument will be there? Please go ahead and let me know. Just now we discussed for ammeter. Now here we are discussing for this voltmeter. We have only three options: critical damping, under damping, over damping.
ये तो अंडर डैम्पिंग लग रहा है.
It's under damping, exactly. Yeah, Sanjeev, you answered that. It's under damping.
Yes. अच्छा सर, एक मिनट. ये
You guys understood? Yeah. Yeah, Sanjeev, go ahead.
सर, ये जो RC और R एक्सटर्नल जो है, ये दोनों मिला करके ही ये क्रिटिकल डैम्पिंग बनता है.
Yes, ये दोनों combine करना पड़ेगा. We'll have to merge all the resistance R coil plus R external, because R external we are connected in series with R coil, right? To
जी सर.
tune or to manage the eddy current damping. And if total resistance, we will have to compare the total resistance with, you know, our critical damping resistance or whatever the total resistance, and then you can get to know the idea behind the nature of damping of the instrument.
अच्छा, डैम्पिंग कांस्टेंट को हम लोग डैम्पिंग टॉर्क कह सकते हैं क्या?
नहीं, डैम्पिंग कांस्टेंट the expression of damping torque is what I have derived here. So ये damping torque का expression हमने derive किया था, right?
टी डैम्पिंग कर सर.
हाँ, T damping का. What was that? T damping is K damping into d theta by dt. Do you recall that?
जी सर.
याद आया?
जी सर.
Yes.
और के डैम्पिंग बराबर बी एन स्क्वायर बटे आर सी प्लस आर एक्स होगा.
K damping, yes, exactly. यही होगा. K damping is equal to B A N square divided by R C plus R external. So
के डैम्प बराबर
हाँ
के डैम्प को ही सर के डैम्प को ही हम डैम्पिंग कांस्टेंट कहेंगे.
Exactly. उसी को बोलेंगे.
Okay sir.
Yes. Okay, so NS has asked one question. In homework, option C say depending on external resistance, damping could be over damped or under damped. Since the expression has RC plus RE in the denominator, isn't that also correct? So now I have discussed all the concepts behind damping. So now you will have to let me know is that correct or not. Or I think this is an assignment problem, but I hope you got it right, because expression has RC plus RE in denominator. So damping will depend on the external resistance. So NS, you can unmute yourself and we can also talk while you are typing. हम लोग हिंदी में भी डिस्कस कर सकते हैं if you want, if you feel comfortable. हिंदी में भी कर सकते हैं. Oh, no microphone, no problem. So next time, please try to fix your microphone. So I hope you got the idea behind it, right? Just let me know whether you got it, the idea behind it or not, what you just asked. This statement, depending on external resistance, we have solved two problems. Is there any other doubt from anyone else?
No problem sir.
No problem. So all of you are able to solve, week 1 homework or assignment?
Yes sir.
Great. That's great to hear. If RE is same as in critical damping case, correct, but they are not saying. If RE is same as in, okay, RE is same as in critical damping case, then correct, but they are not. Okay. I haven't seen the question, but what you can do, NS, you have this email or this Teams or wherever you feel convenient. I'll just see that question and you just message me. I'll get back to you. Otherwise, I'll write my email or just in case if you feel. Do you have my email ID, all of you? On gmail.com. Now,
सर आई हैव टू सम इंक्वायरी. सर जैसे हम लोग दो सब्जेक्ट लिए हैं, इलेक्ट्रिकल मेजरमेंट का और एनालॉग सर्किट का, एनपीटीईएल के थ्रू. तो सर दोनों सब्जेक्ट का जो ऑनलाइन टाइम है वो एक साथ ही हो जाता है. हम लोग को दिक्कत हो जाता है सर. 6 से 8 दिया है टाइम.
अच्छा. तो
सर हम यही चाहते हैं कि दोनों सब्जेक्ट का, तो सर यही रिक्वेस्ट है कि दोनों सब्जेक्ट का अलग अलग टाइम दे दीजिए, तो दोनों सब्जेक्ट हम लोग ये टेकअप करेंगे.
Yeah, I also want to do that, but thing is that NPTEL team manages all the things. So
जी सर, ये आप अपने स्तर से कर दीजिएगा सर.
I'll try, but one alternate option is that you'll have to go through recording. I know that is not the best way. That is not the best way to interact, because in live session we discuss all the queries and questions. But I'll try to figure it out.
Okay sir.
So this is my email ID, and this lectures may be uploaded. it will be uploaded on YouTube. I will try to upload it on YouTube as well. So let me provide the link of YouTube. Okay. So
Sir, excuse me, sir.
yeah, please go ahead.
Sir, will you please explain when we get a critical damping, under damping, and over damping? I couldn't understand. I joined
Okay.
late due to network.
Okay, sure. So I'll just explain it one more time. And anyway, this lecture will be available as recorded on YouTube as well, and you will also be provided with the link of this lecture. But just a quick recap of the nature of damping of these instruments. So what I did, I derived the expression of damping torque. Okay, and this damping torque was damping constant into d theta by dt. So this damping torque depends on the velocity of the pointer. Okay. Now this K damping expression is VA n a square divided by R. And this R is nothing but R coil plus external resistance, what we have connected in this circuit. This circuit was here. Yeah. So this circuit is nothing but this coil is placed in magnetic field, and this coil is also connected with one external resistance, which is there especially for the purpose of eddy current damping. So this phenomena is known as eddy current damping, and here we provide this external resistance, okay, to manage the nature of damping. So the crux of the matter is, I'll let you know, that if the total resistance, and it is very simple, where did it go? Yeah, so crux of the matter is, if the damping constant is higher, the damping torque is higher, right? You agree there? So if damping constant is higher, damping torque is higher, and if damping torque is higher, it means the system will be damped quickly, and your system will be in over damped condition.
Okay.
And that damping constant primarily depends on this resistance. And this resistance we have in our control. So for a meter, we have calculated the resistance, and if our resistance for any instrument is less than this resistance, it means K damping is higher. Do you agree there?
Okay.
Arema, do you agree there?
Yeah.
Yeah. So if K damping is higher, right, it means your resistance has to be smaller than the critical damping resistance.
Okay.
So let me again summarize it. So if your resistance of instrument is higher than critical resistance, what will happen in this condition? Under damped.
Okay.
Our instrument is less than critical resistance, it will be over damped. And of course, our instrument is equal to critical resistance, it will be critically damped. Isn't it?
Okay.
I hope you got the idea. So just go through this recorded lecture one more time, and you'll get it. Okay. Any other doubt from anybody, or you or anyone? No. Okay. So let's move ahead. Okay. I know it is about. Actually, I joined today late. Sorry for that. So.
सर हेलो
Yeah. Go ahead.
सर डी थीटा बाय डी टी का यूज कहाँ करते हैं सर?
d theta by dt, वो damping torque अगर damping torque will be asked in the question, then you'll have to use the d theta by dt. So I just derived this dynamic equation, right? I just derived this damping torque from the dynamic equation. So let me go back to the dynamic equation. Yeah, so this was the dynamic equation, right? This is the standard differential equation. Are you able to see?
Yes, sir.
Yeah. So there I mentioned that with damping constant, this velocity component, angular velocity component will be there. And if you are going to calculate the damping torque, then you will have to calculate b into d theta by dt.
तो उसमें सर ये थीटा का वैल्यू दिया रहेगा क्या इस तरह से?
हाँ, if they will ask damping torque, then they will mention the, in terms of theta, like 5 sine theta or something, or 5 into some theta. So then you will have to differentiate that expression.
ठीक 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 सर.
ठीक है?
ओके.
Okay. So I hope you all are able to understand the concepts behind this dynamic equation and PMMC instrument especially, right? And I hope you are able to solve the question.
सर हम जो असाइनमेंट सेंड करेंगे,
हाँ हाँ
सर हम लोग जो असाइनमेंट सेंड करेंगे तो वो सर उसमें कितना नंबर सही हुआ कितना गलत हुआ ये कैसे पता चलेगा?
They will release the marks, I think, after 1 week or so, or immediately. So वो पता चल जाएगा. They will provide first the answer keys, okay? And after
कब
that
पता
you
चलता
match
है
your answer within 1 week, or I think less than 1 week.
अच्छा सर, सेंड करने के बाद?
हाँ, send करने के बाद भी, even if you do not submit the assignment, then also you will get the answers.
अच्छा ठीक है सर. ओके.
Okay. So next week we will see the questions of the this week one assignment, what you guys are doing, and we will discuss how much of you have made the correct answers and all, and we will see. We'll meet next week. Okay. After deadline on the next day, we can see the result. Okay. So yeah. So according to NS, he said that after deadline, immediately next day you will get the answer. You will see the result. Understood, Sanjeev?
ओके सर. थैंक यू.
अगले दिन ही आ जाएगा. हाँ.
ओके सर.
Okay, so we will meet on next Tuesday. See you then. Good
Okay,
luck.
sir.
Good night. Thank you
Thank
very much for joining. Yeah, thank you.
ओके सर.
night,
गुड
sir.
नाइट आपको.
Good night. Good night. Thank you.
सर
Thank you, sir.
Thank you. Thank you. Thank you, everybody. Have a good night. All the way. Bye.